Okay. All right, everybody. Thanks for showing up, and thanks for being here. And I think we can make this like reasonably interactive, because if you let me drone on, I can do this for many, many hours, but I also can be responsive. So if you have questions, just pop them up, and we'll either tackle them right away, or we'll defer them. So, data preparation. Hardware has been evolving at an amazing rate. Software has been evolving at an amazing rate. Yet there's one constant in the entire IT space, maybe in life: crap in, crap out. And this is where data preparation comes in. And this is why O'Reilly basically termed it the unreasonable importance of data preparation. Everything is about data preparation. At the end, it will always be a result of the effort you put in at the beginning. And everybody loves a good Maslow's hierarchy, me including. So you can see this, and it's actually very topical. Even though it's a couple years old from O'Reilly, you have AI at the very top, which is pretty much the reality of today, right? And the theme of the room here. So I don't want to dive in too much in how data preparation works, but it really starts at source. Particularly when you have streaming data, how you do error corrections, how you fill in missing values, how you start aggregating, how you start pushing it up, especially as data at the source has increased tremendously. I mean, with edge devices like phones, with sensors, weather stations, I mean, data is everywhere, and there's too much of it, and yet there's no information in it. So you want to get to a picture that allows you to get the information you want, which might be different types of information profiles, and that's accurate. And the accuracy, we'll get into it a little bit as we move sort of towards the AI component. So you have all this data, and you have constraints in how you process data. Increasingly, security is a huge deal, and increasing data volume is a huge deal. So one of the interesting aspects we've sort of been looking at is bringing compute to data instead of bringing data to compute. And you get a lot of benefits from that. More efficient stream processing, security compliance, faster error detections, much more robust pipelines, cleaning pipelines, preparation pipelines, all the way to delivery pipelines. Improved latency, there's a lot of advantages. However, there are also some challenges. As data volume grows, it may not fit into a single data center, so you got to spread it across different data centers. Information may go in different types of data lakes. You stream versus batch, real-time versus archival. Performance optimizations of the compute relative to the data are the human skills. If you're data-centric from a provider perspective, what do you have to bring to the table in order to be able to do compute? If you build it yourself, if you bring it on, so there are skill concerns. And then infrastructure requirements. All of a sudden, you may need GPUs, and not just like any old GPUs, but H100s for what used to be considered simple tasks. So there's a lot of challenges in bringing compute to data that may not be necessarily obvious until you actually do it. Now, the actually really interesting part is all the benefits of bringing compute to data accrues to the developer and data owner, and all the costs are accrued by the infrastructure provider. Excuse me. And that's actually not all that easily reconcilable, unless you use Fluence, which is where we're going to go next. So bringing compute stacks brings benefits to different parties. And in DePIN, one of the interesting parts is you bring different parties together, and you build this mesh, this delivery grid, if you will, that transcends individual infrastructure provider. And a lot of the cost components are not, they're lumpy. So if you have to bring in a person to manage your compute, that's a lumpy cost component. You can't easily defray with a billing, for example. So one of the things where Fluence comes in is basically it brings you an entire stack. It brings you the DePIN management component, it brings you the marketplace, and it brings you packaged compute hosting. There are other providers as well. But in addition, Fluence has Aqua, which is a distributed choreography and composition workflow engine, basically. And that, which is not only trustless components, but it actually has, it follows the Zero Trust security framework. So it's actually fully sort of Web 2 compliant, if you will, in cross data center orchestration and composition, which is super important as you start getting into these large distributed data silos, if you will, and to make them one mesh from the compute side. So bringing in a stack like that makes it very easy. And on top of it, it's a general purpose stack. So just for those of you who don't know Fluence, I have one slide on it. We're a decentralized cloudless compute stack, where cloudless basically means no hyperscalers necessary. And we do DePIN, Decentralized Compute Marketplace, and Decentralized Compute Protocols, which allow you to essentially deploy very, very easily, very quickly, general compute runtimes, which are container-based, including WebAssembly. The protocol itself is governed by DAO, the Swiss Association. Those of you who were at Denver probably recall, we issued our token this year. And fundamentally, Fluent's been doing distributed compute since 2017, and some of us a lot longer. So going to the next slide. So how do you actually bring this compute to data? And since I really like the sequence diagram, but they're never particularly readable, let me go to the next one. So basically, you have a data center, and you want to bring compute to data. So the basic flow is you get a data preparation package, which is basically the compute package you get from Fluence, which is it's just basically a binary that spins up and brings all the marketplace connectivity, the chain listeners, the event schedulers, and actually the control plane for running compute. And on the other hand, you have a developer. So I'm ignoring the entire incentivization of DePIN right now. I'm really just looking at the compute part. You bring the developer, and you have this control plane where you now can run your data preparation package, for example, deployed on that Fluence stack, if you will. And right now, if you look, mainnet, so WebAssembly containers are on mainnet. VM workers are on testnet, and Docker, which is finalizing the development. And if you start sort of looking, you end up where the package compute now allows you to bring your own container. And those own containers in the data preparation side, for example, you bring Pandas, PolarS, whatever data preparation package you want. And then with this cross-function choreography, you can build your pipeline, not just within the data center, but across data centers. So you can stitch together a data delivery, processing, and compute layer that's actually seamless across the entire DePIN stack. I mean, literally, if you step back from an entry perspective, it's just another cloud platform built on DePIN. Okay, so what does it actually entail? Where things get interesting now is when you start really looking at where does data come from and where does it go and what is it supposed to do? How is it purposed from object storage? So in this particular write-up, I have sensors. Sensors could be edge devices like your cell phone. It could be a weather station. It could be a surveillance camera. It could be anything at the edge. And this data could go to a data center. On the data center, we have the Fluence package, and on the Fluence package, we have your custom data cleansing and preparation workflows, which are these little containers here. Now, the data center could be actually Docker on Android. It could be Docker on iOS. So the whale is actually Docker on Android, and the blue one is actually Quantum, I think what they're called, which is Docker on iOS. And you can do data pre-processing, you can do data aggregation, and really reduce the flow, the sheer volume of data without losing anything as you start driving object delivery into data lakes, which can, and in the case of people here, could be sitting on Filecoin, should be sitting on Filecoin. And you can drive different flows to different data lakes. They don't have to necessarily be in different data centers, but they could be. And so on the upper one, I have an additional database, which would be, in this particular case, a vector database. And you could drive then retrieval augmentation generation models. You could drive model training and tuning. Or you could literally go and build genetic data generators from this data, which are then used. Since we are in the AI context, all AI use cases. Now, it's somewhat stylized in the sense that what goes where and how is arbitrary, but the point is that you can repurpose prepared data for different data lake scenarios at the source, rather than pushing everything up and then redistributing. That, I mean, massively reduces the bandwidth cost. It massively reduces your retention, and it massively reduces faults and errors. So, since we started with sensors and we had one of the upper examples, this is one of the things I'm working on a lot right now, is basically RAG pipelines. And so I have this overlay where one of the things where Fluence, it's not quite done, but it's very close, actually can run within TE. And you can overlay these TE enclaves across different aspects of your data center operations, of your compute, of your data. And this gives you a lot of optionality in terms of data security, both on the back end and the front end. Now, in order to simplify things a little bit, I'm taking off the TE because I want to get in a little bit how different DePIN projects can come together to really drive AI pipelines, not just from a verifiable blah, blah, blah AI perspective, but literally from a deliverable pipeline that's usable by any project in the AI space, whether it's OpenAI, I mean any. And so you again start from raw data. That raw data doesn't necessarily have to be source. It doesn't have to be the sensor one. It could be the data lake already where you pre-build your objects. You know, and this could be, so it could be cold storage, like Filecoin. It could be hot storage, like Akabe. So this is now on the data center operator side. What do you want to do, how you want to do it, what's the data source, what's the actually inquiry and query model. And then you go, your usual RAG steps where you do the extraction, the chunking, you generate the embeddings, and then you put it in a vector database. Again, you have this data preparation step at this particular case, which is relatively high in the Maslow's hierarchy we showed earlier. It's not at the cleansing part, it's really at the pre-processing, if you will. Now, at the bottom of this, I have the workflow engine, which is actually our Aqua. And in addition, so you're driving the RAG pipeline literally from a decentralized, zero trust, security compliant workflow engine that now drives your RAG pipeline in towards literally up to the response if you want to. And this can be across different data centers. It doesn't have to be the same. So there's no necessary reason to have, just like you have data lakes at different centers, for example, why you have to have the vector database in this particular data center. Yet you can still bring the compute to those data centers and drive this choreography, if you will, this composition with this abstracted, well, not abstracted, but overlay of a composition engine. And then you go into the actual retrieval augmentation, where now you take your questions, you generate the relevant embeddings from your vector database. And as I said, again, this would be hot, so this would be an Akabe scenario, for example. You drive your relevant data, you drive it into your LLMs, and you get your response. And again, you can split this out over different data centers where core competences really start becoming important, right? Because like managing vector databases is slightly different than managing PostgreSQL. Bringing your data close to your inferencing, for example. I mean, those LLMs, I probably should have said this. RAG pipelines are really good to augment inferencing in real time. And it's an alternative or possible adjunct to fine-tuning a model. So a lot of existing models, you can get a lot of traction very, very quickly. You use RAG pipelines to augment their knowledge space, their context. You figure out what needs to stick, you fine-tune the model, you fine-tune your rack pipeline. So rack pipelines in themselves are not static. And this is it's not a flywheel, but it's this virtuous execution process where you keep refining, optimizing, in part based on the inputs and in part based on the delta of the expected outputs. And this is where, again, compute at the data source can solve a lot of problems in terms of latency, in terms of accuracy, and actually in terms of driving costs down. So, since there are no questions, we're getting to the end. Bring compute to data has a lot of benefits. However, the benefits are generally accrued by the data owners and the developers. It creates possibly costs, which are predominantly borne by infrastructure providers. We believe stacks like Fluence can significantly decrease the costs to infrastructure providers. We believe we can bring the capability of creating a seamless compute structure across a massive DePIN underlying network. I believe we can help integrate vertically with data sources and the other way around. And we believe that certain Web 2 components and compliance issues, just as zero trust, for example, are critical in order to enable this. So now it gets a little bit into the business model, who you want to serve, and I think you want to serve everybody, not just Web3. You want to be able to serve the entire market. And for that, you have to somewhat adjust your compliance components. And trustlessness and zero trust have a lot of similarities, but one is actually a deliverable. It's a cryptographic proof system, and the other one is a framework and best practices. So you can intertwine them, and it fits really well both with Web 2 and Web 3. And that's all I got. Thank you very much. If you have any questions, please shoot.
All right, thank you so much. Are there any recommendations or asks that you have back to the community, like specifically Filecoin?
The combination of cold storage and hot storage are super critical, right?
Yeah.
And being able to read fast is imperative. So we've been working on some unsealing sides and been working on it. It's still a little sticky, in my opinion. So really, like, making Filecoin do something it was not necessarily designed to do, either if it's directly or through a Kave overlay, for example. Yeah. This is something we're looking. Same on the interface sides. I mean, we discussed this in Denver. You were there. Molly was there. Wook was there. Charles was there. I mean, almost everybody. Now I'm in the same room again. Different city. We discussed it, and things like, standard APIs like S3 interfaces, for example, and simplified writes. So you can literally write back to the Filecoin system and make it easy for internally. So I mean, Fluence can take care of it, but make it easy to write objects back into those data lakes on Filecoin would be really getting close to the holy grail with Web3 DePIN infrastructure powering a general purpose solution, essentially.
Awesome. Yeah. And that's what we're solving for with Kave. So
I know you set me up. It's not a surprise. I saw this coming. Anyway. But I like it.
No, this is great. I love the workload, like the way you demonstrated the rack, because it's very common pipeline right now that's being used, and I'm just trying to figure out how can we go after this workload together, and kind of highlighted it here.
Talk to me after that.
No, this is great. I think one of the actions here for us is that I take away is maybe help vocalize, bring this to the community as look, this is a way how you can implement a rack pipeline, and then create a reference architecture around that, so that people can actually see how it's done, and then hopefully they will come and then help build with us together.
Yeah.
Anyone? Any other questions?
So how are you thinking about running stuff like NumPy, which is about Python, C, and a bunch of other stuff in Wasm?
Well, hang on. So it's going to be in Docker. It's going to move out from WebAssembly. WebAssembly has not delivered what we thought it would deliver in 2024 when we made decisions in 2019. That's how it goes. But containers overall have evolved in probably the de facto standard of on how to deploy workloads and how to bring portability to the deployment process as well as actually the execution layer. So this is where we're pushing really, really hard. And from the workflow engine perspective, from the choreography perspective, it actually requires very little change. It's just literally on our runtime, we just have to set things up differently to how to interact in the marketplace, how to meter, how to bill, all that stuff. But that's coming really well. And then you're open to anything. I mean, if you can Docker, if you containerize it, you can run it. And then at the same time, we're also adding much more capabilities to manage and sustain long-running containers as opposed to serverless, which is our bread and butter, but we're adding the more long-running things. So you can couple event-driven pipelines with long-running processes, which sort of processing streaming data to me is a long-running process, right? It's ongoing. You keep windowing, you keep windowing, you keep windowing. Processing query-generated embedding extractions from a vector database, to me, that's event-driven, right? So you want both. And the event-driven part, we got down pat. The long-running part, we're adding as part of the Docker containers. So we're actually really, really confident that from our end, we can deliver that as a mainnet capability probably late summer, early fall.
Okay. And in terms of requirements for reading from Falcon, like what are the main drivers? Like would that be is it speed? Is it cost? Because like often the use cases are not really.
So that's a really interesting question, and I think it's a little bit context dependent. Because I mean fundamentally, if you're working with batched or archived data, the expectation of retrieval is probably not event-based, right? I mean, an event might trigger the read, but it's not it's not the latency driver because you're already working off batched or archived data. However, once you get into data lakes, I think you want a lot more responsiveness. And that's something I'm literally looking to you guys in the community to figure out and tell us, or give us, those are the interfaces. These are, this is what we've built, that middle layer of data delivery that, feeds production real-time systems.
Yeah, and would the model where like you define a TTL for the data be something that would tackle that issue for you? For example, you care about the data being hot for the next 24 hours, but you don't care about the data being there after that. Is that something that would work?
Again, it depends on the context. So if you look like, I like general problem solving, universal problem solving, but it never works out all that well. So I've learned over the years that use case driven approaches to start building up. And I think if you're coming from a use case perspective, it's the annoying, it depends. And also what you care about, right? Because, I mean, there are other pipelines you can build. I mean, it's not just RAG. I just use RAG because personally I've been spending a lot of time on it. I think it's very, very topical. And I actually think it's something that's extremely suitable to the overall DePIN ecosystem to deliver, whether it's a decentralized AI or decentralized AI, it doesn't really matter. I just think that DePIN has the mesh capability to deliver RAGs extremely well, and competitively priced. That's part of it. So to answer your question, it's the annoying. It depends.
Okay, thanks.
Sorry.
All right. Okay. Thank you so much, Bernard. Cool.